In example 3, we're going to look at two examples of homomorphisms to learn a little bit more about how homomorphisms work and what properties homomorphisms have. All right, so let's look at our first example, where the homomorphism phi goes from z6 to z6 and is defined by phi of x is 2 times x mod 6. Okay, so the Cayley table is over here, but we can also use a formula to figure out what phi of 0, 1, 2, 3, 4, and 5 are. So phi of 0 is 2 times 0 mod 6, that's 0. Phi of 1 is 2 times 1 mod 6, that's 2. Phi of 2 is 2 times 2 mod 6, that's 4. Phi of 3 is 2 times 3 mod 6, that's 0 again. And then phi of 4 is 2 times 4, that's 8, mod 6 is 2. And phi of 5 is 2 times 5, that's 10, mod 6 is 4. So there are our images of all the elements in Z6. What's the kernel? So the kernel of phi, I'm just going to denote that by k going forward, is all the elements that map to the identity in Z6, which is 0. And there are two elements. So phi of 0 is 0 and phi of, not phi of 4. I underlined the wrong thing. Phi of 3 is 0. So 0, 3, that is our kernel. And note that this is actually a subgroup. This is a subgroup of Z6. So we can look at the left cosets of this subgroup. So let's look at the left cosets. Well, there's the kernel itself, 0, 3. And then if we're looking at 1 plus the kernel, we're getting 1 and 4. And if we're looking at 2 plus the kernel, we are getting 2 and 5. And that's it. So we have our group divided up in our left cosets. So these are the left cosets of our kernel. And let's draw a little diagram to visualize what's going on here. So our homomorphism goes from Z6 to Z6. And we always have two elements that map to the same, that have the same image. So 0 and 3 are in our kernel. So we have 0, 3 in our kernel, and they both map to 0 over here. So both of those map to 0. And then notice that our second coset, 1 and 4, also map to the same element. They map to 2. So 1 and 4 also map to the same element. And then our last coset, 2 and 5, those two elements also map to the same element. They both map to 4. So there's something interesting going on here. The elements in each coset map to the same element in Z6, and then 3 elements don't get hit at all. 1, 3, and 5 we never hit. And so there is a little bit of structure that we can identify right here. Between our cosets and where they map. And a little bit of notation. So we actually say that phi with a little inverse sign of 0, in this case, is our kernel. So that's a set 0, 3. And we call that an inverse image. The book also calls it the pullback of 0. And in a different course, you may have seen this referred to as the pre-image. So Our book doesn't call it that, but I may refer to it by it every once in a while just because I'm used to that from teaching real analysis in particular. So the inverse image of 0 is 0, 3, and the inverse image of 2 is 1, 4, and the inverse image of 4 is 2, 5. So each inverse image is equal to one of our cosets. Let's look at part B of this example. So we are looking at U16, or rather theta is a homomorphism from U16 to U4 and defined by theta of x is equal to x mod 4. And again, we have the Cayley table over here, and I'm going to fill in the images. So theta of 1 is 1. Theta of 3 is 3. Theta of 5 mod 4, that's 1 again. Theta of 7 is 7 mod 4, that's 3. Theta of 9 is 9 mod 4, that's 1 again. Theta of 11 is 3. Theta of 13 is 1. Theta of 15 is 3. So we only have two things that we are hitting, 1 and 3. So our kernel is actually pretty big. Lots of things are mapping to the identity in U4. 1, 5, 9, and 13. 13, I said it right, I just wrote it wrong. Are all in the kernel. So that's our kernel. And then our cosets, well, there's a kernel itself. I'm going to write it down again. And then we have 3K. And that picks up everything else. 3K is the set containing 3, 15, 11, and 7. And again, these two cosets encapsulate our entire group, U16, and we can draw a similar diagram. So first of all, these are our left cosets. So here I have U16, and 1, 5, 9, and 15 all map to the same element over here. They all map to 1. Every single one of them. And then the other elements, 3, 15, 11, and 7, in whichever order I write them, they all map to 3. So my two cosets are the inverse images of 1 and 3. Now, looking at the Cayley table, actually we can look at both of our examples. If you look at the Cayley table, the elements are written in the order so that the elements that are in the same left coset are next to each other. So we kind of have this dividing line right here. So if I divvy this up according to cosets, so my first cosets, if I see the kernel right here, this is our kernel of phi k, and then over here we see 3k, and again here's k and here's 3k. And you can see that all the elements in K, composed with elements in K, just give us elements in K. So we kind of see only elements of K itself sitting right here. And then over here, we are seeing all the elements in 3K. Over here, we are seeing all the elements in 3K. And then over here, we're seeing all the elements in K. So we have this structure that is kind of showing us like a zoomed out version of what's going on when we're just looking at the cosets. And the same thing happened over here. we drew the Cayley table out also so that we have the elements ordered by cosets. And if I draw in these dividing lines, we see a similar thing going on over here. So I have my kernel, I have 1 plus the kernel, and I have 2 plus the kernel. And then here I have my kernel, here I have 1 plus the kernel, and here I have 2 plus the kernel. And we see a similar structure of things that are going on inside the Cayley table. But we will talk about that a lot more in a couple of videos. So if this is piquing your curiosity, hold on to that curiosity. We are going to talk about this some more in a little bit.